Live.
Hello, everyone, and welcome to this next session in the Climate Risk Summit. This session is on tipping points and abrupt climate responses, and I would like to welcome you all very much on behalf of the COP26 Universities Network for joining us today. My name is Erik Mackie. I'm a climate scientist here at the University of Cambridge's Cambridge Zero Climate Change Initiative. And I'm really pleased to be curating this session today. And I would like to, we have a great selection of speakers and panelists lined up for you, and also a great chair. So I would like to introduce you to our chair for today. He's Dr. Shaun Fitzgerald. He is the director of the Centre for Climate Repair here at Cambridge. He's also a fellow of the Royal Academy of Engineering and works at the interface of academic research, business, government policy, and public engagement. So I'm very pleased that we have Shaun today chairing our session, and over to you, Shaun.
Thank you very much indeed. And hello and welcome everyone again from me to this Climate Risk Summit panel discussion on tipping points and abrupt climate responses. Thanks ever so much for joining us for what promises to be a very exciting session. I'd like to start by defining what we mean with the term tipping points. Now, the Intergovernmental Panel on Climate Change defines them as the following: critical thresholds beyond which a system reorganizes, often abruptly and/or irreversibly. Now, the IPCC then also states that abrupt responses and tipping points of the climate system cannot be ruled out, and refers to them as low likelihood but high impact outcomes. That is, the likelihood of crossing a tipping point is deemed to be low, but if we did cross such a critical threshold in the climate system, then the impacts could be catastrophic and far-reaching. In this session, you'll hear from a panel of international academic experts working on tipping points. They'll discuss the latest scientific advances in our understanding of tipping points, including the associated risks and uncertainties, how to communicate those, and how we may prepare for them. First, each panelist will give a 10-minute presentation to introduce and highlight particular aspects of their work. After these initial presentations, we will then open the floor to your questions directed at the panelists. You can start writing your questions in the Q&A box during the presentations, but we won't start answering them until after all the panelists have given their presentations. And I'll be very pleased if you could keep your questions succinct. Therefore, we can also get through as many as possible. So without further ado, I'm pleased to introduce our first panelist and speaker, Professor Rachel Warren. Rachel is Professor of Global Change and Environmental Biology at the Tyndall Centre for Climate Change Research in the University of East Anglia. Her presentation will include tipping points in the Earth system and then talk about tipping points in the ecological system. Over to you, Rachel.
Thank you, Shaun. Could I have the next slide, please? So I'd just like to make a couple of points about tipping points in general. One very important aspect of them is that some of these tipping points then themselves accelerate global warming, which obviously then has serious implications for every other climate change associated risk to human and natural systems. Secondly, there are some tipping points that do not have a physical tipping point, but they can create ecological tipping points, either on land or in the ocean. And that is a strong focus of my own presentation. So Shaun mentioned that tipping points are traditionally regarded as low probability, high impact events, and that's very true. But in fact, it is now emerging that there are some high probability, high impacts as well. The IPCC assessment has looked at the risks associated with these large-scale singular events across its recent assessment reports. And the concern about the potential to cross many of these has risen as scientific evidence has grown. In the special report on 1.5 degrees, a level of moderate risk was assessed to have been reached already, with a warming of 1 degree, which had occurred when that report came out in 2018. That's 1 degree globally, owing to evidence of mass loss from the West Antarctic and Greenland ice sheets. And a transition to high risk was assessed to take place by 2.5 degrees warming, as compared with 4 degrees was the assessment in 2014. So in a timescale of 4 years, the IPCC brought that down by 1.5 degrees, largely due to emerging new literature on the West Antarctic ice sheet. Now, the 6th assessment report will come out during the next 6 months or so. So watch this space for that. Next slide, please. So in 2007, Tim Lenton published a paper basically listing the main tipping elements in the Earth system. And these are listed here. So the Arctic summer sea ice, the Greenland and Antarctic ice sheets, the Atlantic thermohaline circulation, and the Amazon rainforest. These are all tipping points which some of the following speakers will be discussing. They occur over timescales ranging from 1 to hundreds or even thousands of years, and result in consequences such as amplification of global warming, as previously mentioned, sea level rise, regional changes in climate, including to the intertropical convergence zone, and disruption to biodiversity, including biome shifts. Next slide, please. Some of the other tipping elements we don't have time to discuss today. So changes to the El Nino Southern Oscillation, changes to the monsoons, and changes to the boreal forests. But there are actually yet other tipping points about which concern has increased recently. So an important finding from the recently published IPCC Working Group 1 report is that both ocean and carbon sinks are projected to become less effective with increasing CO2 emissions, which would accelerate warming. And in this context, weather conditions that promote wildfire have become more probable in many world regions. Climate change has doubled the area burned by wildfire above natural levels in Western North America. In fact, it was 11 times greater in one extreme year, and burned area has also increased in many other regions, and emissions of carbon have already been detected associated with those wildfires and attributed to climate change. And for this and other reasons, the associated ecosystem carbon losses could substantially raise the atmospheric carbon dioxide level. That is in addition to what humans are doing. And the risk of wildfire transitions from moderate to high risk between about 1.5 and 2 degrees warming. And another concern is about tipping points in the ocean. So climate change threatens the ocean ecosystem through acidification, through deoxygenation. And whilst the effects at the moment are more fragmented, so they're more regional in nature, over time they actually add up to having a global dimension, and hence the new concern about tipping points in the ocean. Next slide, please. I'm now going to discuss some regional examples of ecological tipping points. First of all, the Arctic sea ice has declined by 40% since 1979. Here you can see how it has shrunk from the orange line to the white patch in the last few decades. Next slide, please. And so various measurements of Arctic sea ice area and Arctic sea ice volume have shown these very large declines in recent decades. And this has led to an even larger decline in sea ice dependent species. So some of these have declined by 90%. And at the same time as this disruption to the Arctic sea ice, the Arctic tundra biome is experiencing increasing fire disturbance and permafrost degradation and incursion of woody trees into the tundra. And this overall adds up to an ecological tipping point in the whole Arctic ecosystem, including the sea ice. Next slide, please. The Arctic is projected to be practically ice-free in September in some years for global warming of between 1.5 and 2 degrees, but obviously the chance of that is greater at 2 degrees than it is at 1.5 degrees. And this undermines the persistence of indigenous communities such as the Inuit. A 2-degree warming could reduce the Arctic permafrost area by 15% and release between 11 and 200 gigatons of carbon to the atmosphere accelerating warming. Next slide, please. My second example of an ecological tipping point is coral reefs, where bleaching in the Indian Ocean has exceeded 20% in surveyed locations, and mass bleaching has been reported in all countries in the tropical Pacific, associated with marine heat waves. And 50% of coral within the shallow water reefs in the northern and central Great Barrier Reef has been killed in 2015 to 16. Next slide, please. And this has meant that coral recruitment in 2018 was reduced to only 11% of the average. And this is considered to mark an unprecedented shift in the ecology of the reef, i.e., next slide, please, we are seeing the present day onset of ecosystem degradation in coral reefs, i.e. a tipping point in the coral reef system. In the SR 1.5 report, it was projected that reefs would decline by 70 to 90% at 1.5 degrees warming and 99% with 2 degrees warming. So limiting warming to 1.5 degrees does preserve some of the coral reefs. Reefs are important because they support very high biodiversity in situ. They provide breeding grounds for species living in the wider ocean. And of course, reef fishing supports livelihoods of tropical communities worldwide. And the reefs are very important for national economies. To give the example of Australia, 7 billion per year is the economic value of the Great Barrier Reef to Australia's economy, and it supports the livelihoods of 70,000 people. So next slide, please. So I'm now going to go on to talk about the potential for crossing ecological tipping points globally. So this is looking now basically at a biological system across the whole planet. So when we look at global scale change, we see already that there are increases in pests and diseases, that species are beginning to shift their ranges and they are losing climatically determined geographic ranges because species presence is constrained by the climate and they cannot reproduce in unsuitable climates. Those changes in species distribution ultimately lead to biome shifts, often mediated by changes in fire regimes, which I've already talked about. This leads to disruption of ecosystem functioning and loss of ecosystem service provision, and systems can then reach a tipping point. Next slide, please. So this is looking at global climatic range loss. This is actually from a study carried out in the Tyndall Centre, where we projected the effect of climatic change on the geographical ranges of 125,000 species globally under the Wallace Initiative programme led by Jeff Price. So we quantified the benefits of climate change mitigation for biodiversity and found that with about 3 degrees warming, over half of the 31,000 insects globally would lose over half their climatically determined geographic range. But if warming were limited to 2 degrees, this declines to 18%, and if limited to 1.5 degrees to 6 degrees. Next slide, please. So insects are very important because they are at the bottom of the food chain and perform key ecological functions, for example, pollination. And this slide here is showing the results for pollinators, the key tribes of insects that are responsible for pollination of not only wild plants, but also agricultural crops. And we find very similar numbers to that as we do for insects as a whole. Next slide, please. Similar numbers also emerging for plants, with 44% losing over half their range with 3 degrees warming and much lower outcomes for lower levels of warming. Next slide, please. And similarly for vertebrates. Now, actually, their loss may be underestimated because they are dependent on the plants and insects, and that couldn't be accounted for in the study. But all of these range losses mean large declines in species richness across the globe. And when ecosystems lose species, even if the species hasn't gone extinct but is still somewhere else, the the species richness in every place around the world has declined. And when ecosystems lose species, the ecological functioning, which is underpinned by thousands of links between predators and prey, between flowers and pollinators, between parasites and their hosts, and so on and such forth, begins to unravel. And when enough species are lost, the ecosystem can reach a tipping point and collapse. Now, we don't know how many species have to be lost before such a tipping point is clear. But we have assessed that the risks overall to biodiversity due to climate change are already moderate now, and they transition to high at 1.5 degrees and very high at 2 degrees. Next slide, please. When you look at what does all this mean for biomes as a whole, there are global models that have been run that look at that and look at shifting biomes. We are already actually observing the incursion of the boreal forest zone into the tundra, and we are already seeing changes in biomes in South Africa, where the increase in CO2 concentration is causing the savanna to become treed, in other words, to transition to woodland. And about 30% of the fynbos biome in South Africa is projected to be lost at 1.5 degrees warming, and that goes up to 80% at 3 degrees. And overall, about 6% of terrestrial land is projected to change from one biome to another at 1.5, and at 2 degrees, this rises to 13%. Next slide, please. So to conclude, it may be very useful to design mitigation pathways to avoid tipping points with high probability. So most of the mitigation strategies are designed to reach a certain level of warming. And actually, those levels of warming are generally reached by about 50 or 66% confidence. But these tipping points that could be so catastrophic, you'd really want, 90%, over 90% confidence in avoiding those. And it can be helpful to look at how would mitigation be designed to avoid these tipping points. So thank you. I'll now hand over to the next speaker.
Rachel, thank you very, very much indeed. Right, we're going to now follow that with a talk by Professor Niklas Boers. Now, Niklas is Professor of Earth System Modelling at the Technical University of Munich and leads the Future Lab on Artificial Intelligence in the Anthropocene at the Potsdam Institute for Climate Impact Research in Germany. He's presenting today on observation-based evidence for destabilisation of Earth system tipping elements. Over to you, Niklas.
Thank you, Shaun. Can you hear me all right? That's great. And yes, thank you, Rachel, for this wonderful overview and an introduction to the topic. So I'm gonna jump right in. So next slide, please. With the map, my version of a map that has been, also there's many versions of this map, and you could add some tipping elements here, some potential tipping elements. So with tipping elements, you always mean such subsystems of the Earth system, which potentially have the potential to rather abruptly transition from one stable state to another stable state. And as I said, so there's probably more than the ones I listed here, but we're actually gonna reduce them now because we can't talk about all of them here today. So next slide, please. What I'm gonna show you in the next few minutes are some basic observation-based evidence that these 5 subsystems have, in the course of those last 100 to 150 years, have lost stability, so have approached their respective tipping points, so the critical thresholds at which they might transition to alternative states. And so my approach is when I say observation-based, so it's really the idea of finding appropriate time series that encode the dynamics of these elements. And I see that as a complementary approach to using the comprehensive and, of course, very accurate large Earth system models that we have to model their future evolution given certain greenhouse gas forcing and temperature scenarios. So complementary to that, we're just looking at the observational data, the available observational data of these elements, and trying to understand this from both directions, basically. So next slide, please. So the situation, so the approach is generic in a sense, and it comes from mathematical dynamical systems theory. And the situation that we are concerned about is that we have a system like this, the time series, the blue time series, and it is in one, what we call an equilibrium state, a stable state where it just fluctuates a little bit. And then after some time, it might abruptly transition to another equilibrium state, to another stable state. And the question is, why can this happen? And hopefully it happens because there is characteristic changes in the underlying dynamics. And what you see on top are these double well potentials. So what you could imagine a double well in the small black dot is a marble in there. And so in the picture on the left, it is sitting in the left minimum, which is the left-hand side equilibrium. And then the dynamics changes the shape of this double well when you go to the middle picture on the top. And so the state, the basin of attraction, this is how we call this, has lost stability. It has widened, and then eventually, when we go further to the right, then the whole system isn't even stable anymore, and the marble or the system in question has to transition to an alternative state. The question is, how can we predict this just from parts of the time series prior to the abrupt transition? And there's a phenomenon that is called critical slowing down, and based on this phenomenon, we can define early warning signals for such critical transitions. Next slide, please. And so there are some formulas. If you don't like formulas, it doesn't really matter. It's just to show you that there is indeed a rigorous mathematical theory underlying this. And the key observation is that as the basin of attraction widens, and so the restoring forces for the system decline, or let's say the positive feedbacks that favor a transition, they become more dominant than the negative stabilizing feedbacks. As this happens, the variability of the system increases, and so does the autocorrelation, the memory. So a system state at a given time will become more similar to the state just a time step before, as we approach the critical point, the tipping point. Then next slide, please. So without formulas, what we see here is that indeed the variance and the so-called lag 1 autocorrelation, they increase already prior to the transition, and they can hence be used in principle to anticipate the approaching of such a critical transition. So if you go to the next slide, please. After this little bit of theory and methods, we jump right into results. And here you see 3 columns. The left is for the Arctic sea ice extent. The central one is for reconstructed heights from ice cores from central western Greenland ice sheet. And on the right-hand side, you see a fingerprint time series that is, I think it's exactly very close to the one that Levke, who will talk later, has introduced a few years back, 2 years back, I think. So we have data, observation-based data for Arctic sea ice extent, the central western Greenland ice sheet height, and the AMOC, the Atlantic Meridional overturning circulation. So three of the systems that have often been listed as tipping elements. For the Arctic sea ice, it's not really clear if there are really 2 alternative stable states. It's just clear that there will be a very accelerated response, and then the theory also applies to such situations. So there's no need for this strict bistability for this critical slowing down to work. And what you see in the second and third rows is the variance and the lag 1 autocorrelation, and you see how they all increase, giving an early warning signal that these 3 systems have approached their critical points, or at least indicating that they have lost stability. And if you go to the next slide, please. So for the I'm going to spend 2 more slides on the AMOC, because there's of course the thing that so if we don't know what has happened in the past, and if it would have never transitioned from between different stable states in the past, then I mean maybe this would be questionable how much sense it would make to warn of a critical transition in the future maybe. So what we have here is an ice core from data temperature proxy data from an ice core record from Greenland for the past 60,000 years. And you see these abrupt, so in black, you see the temperature proxy, and you see that these abrupt increases, which are up to 15 degrees within a few decades. So this is sort of the archetype of abrupt climate changes that is actually evidenced in paleoclimate records. And you see that, and theory and our understanding of the climate system suggests that the AMOC transitions play a very crucial role in these temperature fluctuations in Greenland. So it is widely believed that these Danskar-Oeschger events are at least associated, if not caused, by transitions of the AMOC. And what you see indeed is that the variance, which is here the sigma square, and the autocorrelation, which is here this alpha 1, that for most of these transitions, they indeed increase. So we have paleoclimate evidence that these early warning signals are in principle capable of anticipating critical transitions in a process that we link to the AMOC. Then for the next slide. So in the observation-based data, we have the same. We have increasing variance and autocorrelation. So it looks like the AMOC has lost stability continuously in course of the last 100 to 150 years. And then if you go to the next slide, which isn't really the next slide, which is the next part of this slide, please. Thank you. There is this is just as a side remark, and maybe this can trigger some discussion later. So if we just look at corresponding model simulations, then we see that on only 6, respectively 2, depending on what exactly you look at, 6, respectively 2 out of 15 comprehensive Earth system models, they reproduce these early warning signals that we see in the observations. And then next slide, please. So now I'm just gonna again give a few more examples. So we do also see this destabilisation of the South American monsoon system, which we attribute to deforestation and changing interactions between the atmospheric monsoonal circulation and the Amazon vegetation system. And then next slide, please. And also when we look at remotely sensed or satellite-derived vegetation data for the Amazon rainforest, we see spatially quite coherent loss of resilience. So in the map in the center, everywhere where it's red, there we have a decrease in resilience and stability of the Amazon rainforest in terms of these critical slowing down early warning indicators since the early 2000s. And we can attribute this mostly to regions that are drier on the one hand, and regions that are closer to human activity. So the closer you are in the natural, untouched part of the rainforest, the closer you are to settlements, to farming, and so on, the higher the loss in resilience in course of the last 2 decades. And then to the next slide. This is just an outlook, and that's my final slide. So let's assume that we have here some simulations. The black lines are simulations, and the vertical dashed line is the present state. And we have some simulations that where the variance increases and some where it doesn't, and the same for the AC1. And the question is, can we somehow use this observational constraint to narrow down the range of model predictions? So the PDF on the very top right hand side. And then if you go to the next slide, then we look at observations, and indeed, if the observations show a variance and an autocorrelation increase, then if you go to the next slide, and maybe you can just go one more, I think. Yes. So then, no, that was too much, sorry. That was just, yeah. So the early warning signals can help constrain model simulations towards those that are more consistent when comparing to observations. That's the main message here. And then to the final slide, if you to the next slide, please. So the take-home messages, we already defined and explained what tipping elements and tipping points are, and I showed you some observation-based evidence that these 4 or 5 systems that we have focused on, that they show signs of stability loss. So with that, thank you very much.
Niklas, thank you very, very much indeed. We're going to now follow that with a talk by Dr. Sebastian Rosier, who's the Vice Chancellor's Fellow in Geography and Environmental Sciences at Northumbria University. Sebastian will be presenting on tipping points in Antarctica. Over to you, Sebastian.
Thank you, Shaun, and thank you to the other speakers so far. So as Shaun said, I'm going to be talking about tipping points in Antarctica today. And I want to start by looking at this composite image of Antarctica. It's a perspective that maybe many of you might not be familiar with, since Antarctica is typically stuck at the bottom of our world maps. But today I hope to show you why Antarctica is particularly relevant in terms of the Earth's climate system and when we have this conversation about tipping points. Much of what you see in this image is actually seasonal ice cover. But on the continent sit these two major ice sheets, the East and West Antarctic ice sheets. And in many places, the ice of these ice sheets is several kilometers thick. So these ice sheets act as a vast reservoir of fresh water. And altogether, if the entire Antarctic ice sheet were to melt, it would raise sea levels by over 58 meters. And it's this prospect of huge potential sea level rise resulting from climate change that motivates a lot of the research in this region. Next slide, please. So here we can see some of the latest projections for changes in global mean sea level in the coming centuries. The lower blue line represents a sort of best case scenario in terms of future greenhouse gas emissions, somewhat in line with the Paris Agreement, whereas the red line is a more pessimistic business as usual scenario. And the consequences of sea level, longer term sea level rise can be seen here on the left. So this is what I'm going to go on to towards the end of this presentation, this concept of long-term sea level commitment. But you can see that some of these consequences include major flooding of huge metropoli, and some of these represent, for example, in this simulation, approximately 20% of the global population living in these regions. And what I really want to emphasize in this figure is the tremendous uncertainty in those sea level projections. In particular, as we look beyond the next century. So you can see the uncertainty as the shaded regions in these sea level curves. And much of that majority, in fact, much of that uncertainty, in fact, the majority comes from uncertainty related to Antarctic ice loss. Next slide, please. Before explaining tipping points that threaten Antarctica, I just want to make sure we're all familiar with a few bits of terminology I'm going to use. So firstly, West Antarctica in particular is something we call a marine ice sheet. That means that it sits on bed that rests well below sea level. So you can see that represented by this map here, which shows bed below sea level is in the light blue. The schematic on the left maybe helps visualize exactly how that works a bit better. Essentially, the ice sheet starts as snow falling on the continent, and is slowly compacts into ice, flowing under its own weight to the coast. And then eventually it gets thin enough that the buoyancy forces take over the weight of the ice, and it begins to float, forming what we call an ice shelf. These ice shelves are critical and should not be confused with sea ice. They're much thicker, several hundreds of meters thick, and connected to the ice sheet. And they form a crucial role in the cryosphere in slowing down the flow of ice from the continent. And finally, this third point is the grounding line. So the grounding line is the term that we use for the line at which point the grounded ice comes afloat and forms this ice shelf. Next slide, please. So the grounding line is a convenient point to compare mass going in and mass going out of an ice sheet, and that's where we often focus our work. So the mass going into an ice sheet can broadly be categorized as the amount of snowfall falling inland of the grounding line, and the mass going out you can categorize as ice thickness at the grounding line times by the velocity of that ice. So if these terms are in balance, then the ice sheet will not grow or shrink. If you increase, for example, snowfall, then the term on the left goes up and the ice sheet will grow until it reaches a new balance. But crucially, if you have a marine ice sheet that rests on bedrock sloping downwards inland, as shown on this schematic on the left, then there's a possibility of a tipping point being crossed. If something causes that grounding line to initially retreat, it will retreat onto a region where the ice thickness has now increased because of this retrograde bed. That means that the ice sheet is now further out of balance and it will retreat further. And as it retreats further, the ice thickness is yet again even thicker. So in this scenario, a tipping point known as the marine ice sheet instability has been crossed, and retreat will continue until the grounding line reaches a stabilizing feature in the bed. Next slide, please. So we can run models to explore this behavior, and here are two contrasting examples just to point this point home. So on the top, we have a typical case where no tipping point exists. We change some conditions that cause the ice sheet to grow, and the grounding line position, which is shown on the right panel, steadily advances. Now, crucially, if those changes are reversed, then the ice sheet returns to its original extent, as shown in this red outline. In contrast, the panel on the bottom shows the situation where a tipping point exists because there's a retrograde portion of the bed, which the bed is shown as that lower blue line on the left. So here, the grounding line will advance until it reaches a tipping point. At that stage, the grounding line position will rapidly jump forwards to a very new position. And again, if we reverse this change now, in this case, the grounding line does not immediately recover back to where it started. Instead, its retreat follows a completely different trajectory, as you can see here now represented by this loop. And eventually, it will cross a second tipping point where it will return to its original position. And this behavior is something we call a hysteresis. Next slide, please. So many regions in Antarctica are currently undergoing change, and all the evidence points to this being driven largely by changes in ocean conditions. Mass loss from Antarctica tripled between 2012 and 2017. And here we can see the mass loss represented by these red circles on the map on the right. The floating ice shelves that I introduced earlier can be seen as the colored regions on the map. And you can see that what really stands out is that this region on the western side of Antarctica, where you have very large mass loss. And that coincides with, as shown on the left, these regions where warm, deep water from the surrounding ocean can get onto the continental shelf, and it gets access to the deeper parts of the ice sheet where it's most vulnerable. So there it melts the ground, melts away at the ice, thins the ice shelves, and causes the ground line to retreat. And one region we're particularly concerned about is the Amundsen Sea embayment, which is in the sort of center of that region. Since not only has this seen the most dramatic changes, but the glaciers in this region are resting on retrograde beds, which makes them susceptible to the marine ice sheet instability. Next slide, please. So in some work published this year, we showed for the first time that this marine ice sheet instability tipping point can indeed be crossed in this region of Antarctica, specifically the Pine Island Glacier. Here we show the sea level curve as a function of increasing ocean melt, and you can see the retreat of the glacier is split into several stages. In fact, each of these stages represents a smaller tipping point, preceding the final tipping point, which you can see more clearly on the right-hand figure, that causes the entire glacier to collapse. This result challenges a more traditional binary view that glaciologists have ever had, that a glacier is either a tipping point, either causes a glacier to collapse or not, and emphasizes the difficulty we have in modeling these processes where only a small change in conditions could cause the glacier to cross a tipping point. Next slide, please. Now, I've been talking about one glacier in Antarctica, so you might be justified in thinking, is that really a cause for concern? If we can play this video on the right, hopefully that should start showing an animation. Anna, okay, let's go back. Don't worry, the video is not crucial. If we can go back to the previous slide. So work from a group in Potsdam showed that retreat from this glacier, which is outlined in white, would actually lead to a collapse of the entire West Antarctic ice sheet. And if this video was playing, you would be able to see how that leads to this large-scale collapse. And then we're talking about very significant amounts of sea level rise resulting from that. And to just hammer this point home, you can see the resulting sea level curves for either stable or unstable retreat on the left as red or blue. So you can see how stark the difference is in those responses. Next slide, please. Now, given the importance of this topic and how much research has gone into it in recent years, why were those graphs that I showed you at the start so uncertain? Where does that uncertainty come from? Well, a large part of the problems we face in glaciology relate to Antarctica's remoteness and its size. This makes it incredibly costly and time-consuming to collect, for example, the radar data, which gives us measurements of ice sheet thickness that our models rely on. It also pertains to just the acquisition of data itself. So, for example, conditions of the bed of the ice sheet are crucially important to understand, but the bed of the ice sheet sits below several kilometers of ice. So we have extremely expensive data campaigns to try and observe these environments, but that remains a challenge. And finally, on the right, you can see, unfortunately, again, not playing the video, but these poorly represented processes. Here we go. So these are poorly represented processes on a model, which are really at the cutting edge of our understanding, fracture and ice shelf carving. These are all processes that are a real challenge to incorporate into our models. Next slide, please. And there's one more wildcard in this story, which I haven't talked about, and I don't have time to talk about, unfortunately, and that's a second possible tipping point mechanism, which we call the marine ice cliff instability. So this is kind of similar to the marine ice sheet instability in some ways, but it's a huge source of debate in the community at the moment. And there's very marked difference in sea level projections for models that include this mechanism as against those that don't. And you can see that difference on this panel on the left. So you can see sea level projections that include that mechanism as the dashed lines. So a very different response. And next slide, please. So I want to finish today just talking about what I think is a really important concept, and that is this concept of committed sea level rise. So an ice sheet inherently responds extremely slowly to changes over very long time scales. And this slow response, together with the existence of tipping points, means that we don't have the luxury of only worrying about sea level rise over the next century. Even if we rapidly reduce CO2 emissions, as you can see on the left scenario, and global mean temperatures were to stabilize, as you see in the center, the Antarctic ice sheet will continue adjusting to its new climate for millennia, committing countless future generations to having to deal with the consequences of our actions today. And again, because these tipping points exist, even if we were to return to the climate in its pre-industrial state, the ice sheet would almost certainly not recover to its pre-industrial extent. And so sea level change and the loss of coastal communities becomes effectively irreversible. And that's all that I'm going to say for now. Thank you.
Sebastian, thank you ever so much indeed. I'm reminded of two things. The great thing about some of these responses you're talking about is that they take a while to unfold, and therefore we've been insulated from the effects. The terrible thing about some of these effects is they take a long time to unfold, and therefore actually what we're looking at are just dramatic changes over long periods of time, and hence we need to get our, basically get a grip on the situation and do something about it. So there are pros and cons, and there are clearly many more cons. Let's not kid ourselves, this is absolutely terrible. So look, what I would urge the audience to do, please, because we're going to be moving to our fourth speaker, is to actually go and sort of get onto the chat. If you've been stimulated by the materials thus far that have been shared by our excellent presenters, please do throw some grenades at them in the form of nice questions. Keep them succinct, as I said, but we would love to have a stimulating conversation really spawned from your questions for the latter half of this afternoon. So without further ado, we're now going to move to our next speaker, who is Dr. Levke. She is a postdoctoral researcher at the Irish Climate Analysis and Research Unit at Maynooth University. Her presentation today is on When is the Day After Tomorrow, about the past, future and potential tipping of the Atlantic overturning circulation. Over to you, Levke.
Yes, thank you for the introduction, Shaun. Yeah, as Shaun said, basically you could say that one of the big science questions I'm dealing with is the question, when is the day after tomorrow? That's my title slide, and we're going to the next slide right away. So for those of you who don't know, The Day After Tomorrow is a Hollywood blockbuster from 2004 in which filmmaker Roland Emmerich portrayed the disastrous effects of an abrupt climate change, namely the shutdown of the overturning circulation in the Atlantic. And as a consequence, there are suddenly numerous tornadoes in Los Angeles, a massive wave hits Manhattan, and several days of severe snowstorms covering the entire northern continent lead to a new ice age. Luckily, we can say it's easy to dismiss much of this scenario as unrealistic and exaggerated, starting with the fact that when climate scientists talk about an abrupt climate change, they are rather talking about years to decades and not just a few days or weeks, which is the time period covered in the movie. But despite these scientific inaccuracies, the movie actually presents a real mechanism, which is the possibility that the overturning circulation in the Atlantic, which we refer to as AMOC, may shut down. But before I talk more about its shutdown, let's have a quick look at what the AMOC is. And yeah, please play the video now. So the video I'm going to show you is by NASA, and it's going to, no, that's not it. It's going to portray the flow of the AMOC. Can we go back to the video? Maybe I kind of start off. So the AMOC is, it's important to note that it's not a single current like the North Atlantic current or the Gulf Stream, but it's actually a system of different currents. And it covers the North Atlantic, and it would be really nice if we could play it. If not, then I would just rely on your imagination, kind of try to picture the North Atlantic. And the AMOC is the system of currents that oh yeah, now we can see it, great. So It's the system of current that is characterized by a northward flow of warm and salty waters in the upper layers of the Atlantic. And sadly, we kind of missed the first part of the video, which really nicely portrays that. And well, the important part is that these water masses, as they are transported northward within the Atlantic, they cool down because they're releasing heat to the colder atmosphere above it, and they become denser and therefore sink to deeper ocean layers, where we then see a southward return flow of these colder waters. Maybe we can just start again, or maybe not. And this inflow of warm surface waters in the upper layers of the Atlantic towards the north and the outflow of colder deep water lead to a redistribution of heat by the circulation. Yeah, this is great. Bringing heat from the tropics to the high northern latitudes. And we're talking about a lot of heat energy here. So the maximum northward transport that occurs in the subtropics sums up to about 1.3 petawatts. And yeah, this is what you're seeing now. This is the sinking of water masses. We call it deep water formation that is crucial in driving the AMOC. And this, as I said, inflow, warm water, outflow, cold water, massive heat transport. And as it's released to the atmosphere over the North Atlantic, this large heat transport has a huge effect on the climate in that region, including Europe, and is, for example, one of the main reasons why the northwestern European winters are on average about 10 degrees warmer than the ones in Canada, even though they are located at about the same latitude. Therefore, a shutdown of the circulation system would indeed lead to a cooling, as well as other changes in the northern hemisphere, but in a different way and on much longer timescales than was indicated in this Hollywood blockbuster The Day After Tomorrow. So now we're going to the next slide, please. So basically, all state-of-the-art climate models predict a weakening of the AMOC over the course of the century in response to global warming. And what you can see here are the projections of the AMOC strength in the latest intermodal comparison project, that is the CMIC-6 project, from 2000 until 2100 for different CO2 emission scenarios. And while you can see that there's a large spread in AMOC mean strength and variability between the different models, they all show a weakening of the AMOC with a best estimate of 34% for the low emission scenario and 45% for the high emission scenario. And this predicted future decline of the AMOC is actually not surprising, as there are several processes in a warmer world that lead to a decrease of the deep water formation in the North Atlantic, that is the sinking of water masses that you just saw in the video. And this is a very important driver of the overtonic circulation. So when it decreases, this will weaken the strength of the AMOC. Next slide, please. So the processes causing a weakening of the AMOC include sea ice loss in the Arctic that we already heard about. So here in the upper left, you can see the sea ice extent has been reduced drastically since the 80s. Then the melting of the Greenland ice sheet, which you can see in the upper right, which affects an increasing area of the ice sheet. And then also increased precipitation over the high northern latitude that you can see here in the lower right. And these processes all have in common that they lead to an increased freshwater flux into the subpolar North Atlantic. And as freshwater is less saline and therefore less dense than normal ocean seawater, they lighten the surface water and make it harder for them to sink. And another factor that hinders the deep water formation under global warming is the actual warming of the upper ocean. In the middle here, you can see the temperature trend over the last approximately 150 years. And this warming too will make the water lighter and therefore less likely to sink. By the way, this blue region south of Greenland, which in contrast to the rest of the world cooled over the last century, is likely linked to an already weakening AMOC. But I will talk about that in a moment. In general, you might have noticed that even though I talked about a predicted future AMOC weakening, most of these processes causing the weakening are already ongoing. And this leads to the question whether the weakening of the AMOC has already begun. But answering this question is not that easy, as direct continuous measurements of the AMOC only started in 2004. So the resulting time series is too short to answer questions about any long-term trends in the AMOC. So for any information about the AMOC before 2004, we have to rely on so-called proxy data that are climate variables that are directly affected by the AMOC and can therefore be an indicator for its strength. Next slide. One example for such a proxy data for the AMOC are the sea surface temperatures in the North Atlantic, as they are highly affected by the AMOC. So on the left, you can see the modeled response of an AMOC slowdown by about 25%, as we can see it in the sea surface temperature trends. And you can see that the reduced northward heat transport that is linked to a weaker AMOC causes a relative cooling of the ocean south of Greenland. And at the same time, the dynamic response of the Gulf Stream to a weaker AMOC, which is a little bit more complicated, but it basically leads to a shift of the Gulf Stream to the north, causes enhanced warming of the US East Coast. And when we look at the evolution of the real world temperatures, here seen at the right-hand side over the last century, you can see that we basically see the same pattern. So the main difference is that the resolution of the observational data is less than that of the model, and the data is in general a little noisier, but it's the same pattern or fingerprint. And when we analyze the amplitude of the signal in more detail, we get an estimate that the AMOC slowed down by about 10 to 20% since the 1950s. So, I mean, basically the nature of a proxy is it's a proxy, so it's not a perfect representation of the system. So you might not want to trust a single proxy, which is why we also looked at other kinds of proxies, which a few of them go even way further back than this sea surface temperatures, and we found a similar picture. Please go to the next slide. Okay, here, please don't be confused by all the different panels. Basically, they're all climate indicators, mainly found in ocean sediment cores, that are linked to the AMOC in very different ways. So this reddish purple data, for example, comes from coral shells, and it's an indicator of the subsurface temperatures in the subpolar North Atlantic. The green data gives the grain sizes found in ocean sediments, and there, because faster currents can carry larger grain sizes or larger grains with it, an indicator of the strength of the deep water branch of the AMOC. And all these proxies are, for a better comparison, plotted against the sea surface temperature-based reconstruction of the AMOC that I just talked about, which is shown here in shades of blue. And as you can see, while these proxies show some differences in their multi-decadal variability, they agree well on the fact that the AMOC has been relatively stable prior to the 19th century. And after this long stable period, all proxies show decline starting sometime in the 19th century. And it follows a second, more rapid decline somewhere in the middle of the 20th century, so around the 50s, 60s. And together, these lead to the AMOC over the last decades being in a weaker state than ever before over this time period for which we have proxies. And combining this with predicted future decline, this could take us dangerously close to the tipping point of the AMOC. And next, my last slide, please. Yeah, I just want to sum this up with the latest IPCC, with what the latest IPCC report said about an AMOC weakening, kind of stating that it will very likely weaken over the 21st century, saying that it's unlikely that it's going to shut down or collapse, but also stating that such a scenario, that is a shutdown of the AMOC, remains a physically plausible scenario, even for the course of this century. And indeed, it appears that climate models in general tend to have a too stable AMOC and might therefore underestimate the possibility of a shutdown. So we really have to be careful here. And furthermore, it's important to note that such a shutdown would be a high impact scenario, leading, for example, to a decrease in marine productivity in the North Atlantic, increasing the number of winter storms in Europe, affecting the Asian and African monsoon system, and enhancing sea level rise along the US East Coast. And with that, I want to thank you for your attention.
Levke, thank you ever so much indeed. So we're now going to move to our panel Q&A. Again, I would urge the audience to pop in some questions into the chat, try and keep them succinct, and then similarly our panelists, if we can keep the answers to these questions relatively brief, we're going to be able to field as many questions as possible that have already been given and ones which will hopefully then be given. Right, we're going to start with a question from Herbie Bradley. In the Working Group 1 contribution to AR6, which came out recently, the science showed a decrease in the top end of the climate sensitivity range from AR5. Does this mean the risk of extreme warming, let's say above 4 degrees, has decreased, and that the risk of triggering some tipping points which come into play at high levels of warming has also decreased? So who would like to take a stab at this? Rachel, we just need to get you to unmute. I think we went unmute and then mute again. So Rachel, we'd love to hear from you.
Okay, so thank you. So yes, so what actually happened in the recent IPCC report is that the the scientific evidence has allowed us to estimate the value of climate sensitivity more accurately. It's not really that we think the Earth's climate sensitivity is smaller than it used to be. That's not true. It's that the range of uncertainty around the most likely range that we previously had estimated has decreased. So that means that not only has the right-hand tail come down, but also the left-hand tail has also shrunk a little bit. So you need to remember that not only has the probability of very high warming gone down a bit, but also the probability of very low warming has also gone down a bit. So I don't think that there is really any cause for complacency as a result of that. The other point I would mention is that the temperature ranges for many of these tipping points are all well within the range of plausible temperatures that we could reach by 2100 in most cases. And it does not require these very large values of climate sensitivity for us to trigger these tipping points during this century.
Okay,
so,
Rachel.
In short, I don't think that there are really any policy relevant implications in the sense of, well, perhaps we don't need to be so worried about these. I don't think that it makes any difference to the policy implications.
So I take, Rachel, what you've just said. The second question that Herbie asked, the answer is no. In other words, does the risk of triggering some tipping points which come into play at high levels actually decrease? I think what you're saying, Rachel, is no, that's not the case. We're actually, the risk of anything, we've got greater understanding that these really are a real issue, which is germane to the conversation today. Right.
Yes, absolutely. We've also got much more evidence on the all of the speakers today, many of them have been presenting evidence that some of these tipping points have already been triggered.
Exactly. Right, we're going to move to our next question, which we're going to take from Kyle, which is along the following. Are there any technologies in their infancies that would be able to reverse the loss of sea ice in Antarctica? So we're going to throw that open to the field to start with. Who would like to take a stab at this? And if not, then I'll probably put my own hand up. Okay, so right, very briefly, there are technologies in their incredible infancy being looked at because, you know, worrying about just emissions reduction. We've heard about inertia in the system already, and therefore we're very, very concerned that just emissions reduction may well not be sufficient, certainly necessary, but not sufficient to avoid some of these. And therefore, there are some thoughts regarding what we might need to certainly learn more about things like solar radiation management to be able to then try and reverse some of this. It's not stuff that we should be deploying right now because, frankly, we don't know enough about it. So we need to further our knowledge first before we can make an informed decision as to whether that may or may not be a sensible thing to do. So that's my 2 pence worth, as it were, in terms of trying to address that question. Right, the next one, we're going to have a question from Luke, which is, how could the risk management of tipping points be incorporated into both international law and domestic policy making in the UK? Who would like to take a look, take a stab at that one?
Maybe I can start off here.
Levke, that'd be great. Yes, please.
I would say in general, maybe you should look at the priorities. I mean, basically, avoiding the risks of tipping points would obviously be general kind of saying, okay, we have to lower global warming, we have to get our emissions down. And I mean, these are the things we should probably tackle first. And in terms of risk management, basically you just have to keep track of them, right? When you have a risk of increased sea level rise, this doesn't really, I guess it doesn't really matter in the sense of where does it come from? Does it just come from general warming and thermal expansion of the ocean? Does it come from glaciers? Does it come from something as Antarctica? It's going to be a sea level rise. I guess the main point is with the tipping points that they increase a really large range of uncertainties, because they would, if they happen, just suddenly, as you saw in the slides by Sebastian, they would increase the amount of sea level, for example, by a lot. So in that sense, I would say it's important to make, and I always thought that a lot of people already know about it, but it's kind of, I guess it's a misconception from the people I know. It's really just important to keep them in mind as we call them this low risk, high impact scenarios. And now we kind of have to see it's maybe even medium or high risk, high impact scenarios. So I guess it's important to always incorporate them. But in general, I mean, it's probably not that different from how we would normally have to tackle climate change. Yeah.
Understood. Right, we're going to take another. Yeah, Sebastian, do you want to chip in on this one?
Yeah, just briefly. I just think I think there's an issue that a lot of scientists in climate science face, where you don't want to be alarmist and you don't want to overemphasize a risk if it's potentially a low probability event. But equally, these should be emphasized in the sense that you have to try and to some extent prepare for the worst case scenario. And you know, when you design an aeroplane, you don't design it to just about manage to get in the sky most of the time. You try and make sure that every single time it's going to fly successfully. And so I think these low probability, high risk events have to be considered as crucial parts of policy in the future.
I could not agree with you more strongly. And Sebastian, whilst we've got you, Studio have let us know that the video that you were trying to show in your presentation is actually now fixed, as it were. So could you just talk us through that? So for Studio, if you could put that on the slide, it'd be great if you could just talk us through that, please, Sebastian.
Yeah, absolutely. Yeah. Yeah, here we go. So yeah, this is some work done by a modeling group in Potsdam. And as I said, the idea here is that this glacier, Pine Island, which is where the retreat started, can, even though it's initially just the retreat starts in this one glacier, as that glacier starts to thin, it affects neighboring glaciers, the drainage basins that feed them. And that retreat you can see spreading. The black line marks the grounding line, so this is ice effectively becoming afloat, and you can see on the bottom the sea level curve that results from this this spread of that melt across the whole of Western Antarctica. So although one individual glacier may not be a cause for concern in terms of its individual contribution to sea level rise, there is the possibility, as we say, this weak underbelly of Antarctica, that that one glacier's collapse could trigger a collapse of the entire West Antarctic ice sheet. And then we're talking about extremely significant amounts of sea level rise in the future.
Well, Sebastian, thank you ever so much indeed. And that does lead us very nicely to a question from William MacDonald. And it's a little germane perhaps to the next session as well. But the question is as follows. How do we take account of the interaction of tipping points? Are Earth system models capable of predicting how the breakdown of one system would affect the functioning of another? So I think this might be relevant for a number of people who might wish to comment on this. Who's going to go first?
I can give it a try.
Great, Niklas.
It's very difficult. So I mean, these elements are extremely nonlinear. So, and Levke is already for the AMOC. Levke has mentioned that there is a suspicion that the AMOC is in current models is still too stable. So there might also be other of these other examples of tipping elements which appear too stable in the model simulations. And then on top of that, really modeling the interactions between such highly nonlinear systems is extremely difficult. And one example is, so there's a collapse of the AMOC from the current strong state to the weaker state that has been occupied the last time during the last glacial interval, that will heavily impact sea surface temperatures in the tropical Atlantic Ocean, which will affect the West African monsoon, but it will also affect the South American monsoon and basically the pattern, the spatial and temporal pattern of rainfall in tropical South America. And well, I mean, we all know that the Amazon rainforest heavily depends on that rainfall pattern. And so let's say up to 10 years ago, most models that were used to analyze this question, they suggested an increase in rainfall in the tropical South American region where the Amazon is, and then more recent higher resolution model simulations from the Met Office, they actually suggested that the rainy season precipitation decreases, but the dry season precipitation increases, and then how that in fact really affects the Amazon rainforest is an extremely hard question to answer, which we don't know the answer right now. So at the moment, I would say we are not certain whether a collapse of the AMOC would actually trigger a collapse of the Amazon rainforest, or whether it would indeed stabilize the Amazon rainforest. So these are, I mean, it's extremely relevant to understand these interactions. And of course, it also, the critical forcing levels of one tipping element like the Amazon rainforest crucially depends on the state of all the other tipping elements that might affect that Amazon rainforest. So basically just giving single numbers doesn't make sense in this context, because it really depends on the state of all others. So it's a very relevant question, a brilliant question, and the true answer is, I mean, this is what we're really trying to work on, but we don't really know the answer now.
Absolutely. Does anyone else want to chip in on this or not?
Sorry, you go ahead.
Levke, go on.
Okay, I would go first in the sense, if we look at the prediction for the 21st century, then this often does play a big role, because a lot of the tipping elements, even if they do tip, they take a lot of time before they actually get to a shutdown, melting or whatever. If we look at the next couple of 100 years, then this plays, of course, a large role. I know there are like some first studies with not that complex Earth system models that try to model these effects, but here it's also important that it really depends on basically the order. When does the first, or which element will tip first? For example, a shutdown of the AMOC could actually lead to a stabilization of the Greenland ice sheet, because a shutdown of the AMOC would lead to a cooling in the north. But it would probably destabilize Antarctica. On the other side, when we first have basically cooling in the north and a shutdown of the Greenland ice sheet, suddenly, when we first have the melting or the collapse of the Greenland ice sheet, and suddenly it hence warming there, this could on the other side destabilize the AMOC. So this really depends, as Niklas said, it's highly nonlinear. It really depends on which element starts to basically change first and at what rate. And so it's a really complex question.
Great. Well, in which case, let us move to the to another question. So we have another question now from Craig Hutton, and that is, I mean, clearly, somebody mentioned that we don't have that much data, but we would like to look back in time. Are there any historical collapses in AMOC that we can use as an analog, and certainly to further our understanding, therefore, of what might happen in the future? Does anyone want to take a stab at that?
Yeah, I think in one of my slides, I showed a picture of that essentially answers that. I'm not sure if it makes sense to bring that up again.
Let's do that. Let's do that, Niklas. Which slide? Studio, can you help with this? So this is Niklas's presentation. Do you have an understanding of which slide number?
Should be slide 8.
Slide 8, Studio, for Niklas's.
I hope so.
The large pregnant pause here.
So, I mean, I can already start explaining
yes.
why I showed that slide. So essentially, I mean, really understanding what happened in the past is, of course, key to being able to predict what's going to happen in response to anthropogenic climate change, although that, of course, hasn't happened in the past, the anthropogenic part. So this is what we're looking at is a part of the last glacial, so colloquially the last ice age, which stopped around 10,000 years ago and started around 110,000 years ago. And as I explained earlier during my talk, so what you see on the top in black is a temperature reconstruction from the summit of Greenland, of the Greenland ice sheet. And these jumps that you see, they are most likely, I mean, to all what we know, they are associated with transitions of the AMOC from the weak to the strong mode and vice versa. So we do have a lot of evidence, I mean, quite strong evidence. I mean, this is just one time series from an ice core, but you can also look at ocean sediment cores that are more direct proxies of AMOC variability, which also give you the same answer, that the AMOC has switched repeatedly from between two stable states to two circulation modes in the past, mostly, I mean, in the last glacial. The problem is that the data to really understand the impacts of this globally, the data is very sparse, because we're talking about time spans of things that happened 20, 30, 50,000 years ago. And it's really hard to estimate the exact impacts beyond statements like how it will affect the overall the Indian monsoon system or the West African monsoon system. So on a large scale, we can have some estimates, and this includes what this information goes into what Levke said at the end of her talk, basically, that we have disruptions of the West African and of the Indian monsoon. But so it's really only at the large scale that we can draw conclusions on the impacts of an AMOC collapse from past paleo reconstructions.
Great, thank you ever so much indeed, Niklas. Now, Rachel, we have a question that I think is probably going to be best for you to tackle. It's from Antoine Libet. Are you aware of discussions on identifying tipping points for agricultural pests and disease? I hope I haven't put you in it, as it were, Rachel. Do you feel comfortable to tackle that one?
Sure, yes. So, okay, well, short answer is no, I'm not aware of specific discussions about tipping points for diseases in and pests in agriculture, but I am aware of the large amount of work that is going on this. And indeed, even within our own Wallace initiative, we've been modelling the projected changes in the geographically determined climatic range of some of these pests in particular. So as you saw in my presentation, that, we were finding that typically, about 50% of species are projected to lose half their range with 3 degrees of warming. Actually, what we also find is that a very small percentage of species are projected to increase their range dramatically. And guess what? Quite a lot of those are pests and diseases. So there are plenty of groups looking at this. Of course, we've already seen some new pests and diseases coming into the UK in both natural and agricultural systems. And so, given the potential for loss of ecosystem functioning that I was talking about, these pests and diseases can wipe out, for example, key tree species. So we're seeing a lot of new pests and diseases attacking trees in the UK at the moment. And some of that has actually come in because of horticultural trade and not because of climate change. But there are actually quite a lot of insects that are colonizing Britain as a result of changes in climate. And so certainly that can include agricultural pests, some of which have already been seen to be increasing. So this is certainly a serious issue and could indeed be one of these hidden risks that we're not really aware of. So yes, that is a risk, but I would say it's an emerging risk that we don't know much about yet.
Great. So I'm going to ask the audience to keep throwing the questions into the chat function. So we will be able to get to you, even if you're late to the party, as it were, in terms of throwing some questions. But our next one is actually related to changes in the Arctic. And we had a conference here in Cambridge yesterday. We're basically looking at the topic of methane. Haven't heard huge amounts today regarding, gosh, in terms of tipping points and what might happen in the Arctic regarding changes there, and therefore how do we go and look at what kind of temperature rise, what kind of changes might we need to see before we then see unprecedented releases of methane in some form or the other. Would anyone like to take a crack at potentially sort of giving some commentary on at least that particular topic? So in terms of any modelling that people are doing, has anyone looked at this? Well, it's Niklas,
maybe just, I'm not sure. This is not going to be an answer. I'm apologizing in advance. Just a comment that so the reason why none of us has really maybe not looked at in detail at modeling the methane. There's this Arctic permafrost methane release thing that is often listed as a tipping element. The point is that it is not really, in a strict sense, there's some who don't think it is really a tipping element, but what we're looking at is a positive feedback. So of course, the warmer it gets, the more melting we have of the permafrost soil, that releases more methane, and that will lead to further melting. So there is a positive feedback, which is important, which is dramatic and which increases global mean temperature rise, of course, or it enhances global mean temperature rise, but it is not a tipping element in the sense that basically the line at which we have 0 degrees where the melting takes place, that will still move gradually towards the north. So the permafrost spatially, this will not be really an abrupt, like in the sense where abrupt in the sense as we look at other tipping elements. This permafrost isn't the permafrost melting isn't probably as abrupt as other elements.
Does anyone, Rachel, would you like to have a comment on this?
Yeah, so I'd just like to say that, yes, so I agree completely with what's just been said. In my presentation, I also emphasised that some of these transitions that are not defined as physical tipping points can then have non-linear consequences for everything else. And obviously, of course, if we did have a large release of, so in my presentation, I mentioned the potential for loss of permafrost leading to between 11 and I think it was 100 gigatons of carbon lost to the atmosphere. Some of that loss was actually due to methane.
Okay.
And basically, so there's a very wide estimate around there because there are quite large uncertainties at the moment in how much carbon would be released for how much warming and how fast. But clearly, if warming was accelerated like that, it would have very, very serious consequences. You know, the whole Paris Agreement and the setting of the 1.5 degree temperature goal is founded on the accumulated evidence about, you know, to what level of global warming do we need to limit in order to avoid impacts. And clearly, if with 1.5 degrees warming, we would still see a huge feedback of some kind, then it means that achieving the Paris Agreement would not achieve what we want it to achieve. Now, if that were the case, it doesn't mean that we should give up on it. It actually means that we would need to try to do even better than the Paris Agreement, which would probably be regarded as not feasible. But yes, so we would be in a very, very bad situation indeed if that release of methane were to be triggered below 1.5 degrees. So now, I mean, obviously with those large uncertainties, it could be that a large release might not happen until much larger levels of warming. And I'm not really expert in, you know, what the latest literature says about precisely how much would be released at precisely what level of warming, and perhaps there are others on the panel who are. But clearly this is something we really need to be very careful about and try to gather evidence for whether this methane is already being released or not. And my understanding is that the observational record on that is showing that methane is being released, but that because the record is not very long in time, we don't know whether this is or is not unprecedented.
So, Rachel, you've stimulated a thought. Really, you know, you said, look, what we know now, 6 years after the 2015 agreement and the 1.5, and we're on the topic of tipping points today. Is it possible that actually even 1.5 degrees C is unstable? In other words, is it, you know, we've set this as a goal in 2015, given what we now know and the sorts of changes that basically can unfold, is it possible that even a 1.5 degrees C might be a target, but is it a stable target?
Yeah, I don't think we know completely.
Right.
So, and clearly, what I can say is that if we didn't make 1.5 degrees and we were at 2 degrees, it would be more likely that that would be unstable. Okay, so basically, the message is the more we limit warming, the more likely whatever we limit to is likely to be stable.
And is that a message that perhaps could do with some amplification, given the topic of today? Great. Right. Some further questions. Let me just go down to the back to the. We have a question from Erik, which is as follows. For policymakers trying to plan ahead for the future in terms of adaptation, how should they deal with or factor in the large uncertainties associated with tipping points, e.g. when building coastal defences for future sea level rise, or building codes and things like this in terms of where you put your plant? What is it that policymakers should be doing? So who would like to take a stab at that?
I mean, I can jump in briefly. I mean, in terms of sea level rise, we do have, to some extent, an advantage in that at least Antarctica does respond relatively slowly to this. So, as I said, the uncertainties in our projections get rapidly larger as we look further into the future. But if we're talking about really large meters and meters of sea level rise, then we're talking a very long way into the future. So I think my view on this is that, as was mentioned just now, I think we should aspire to be cutting back on emissions as much as possible. And this attitude of, well, what can we get away with is entirely the wrong way to be tackling it. We should be immediately cutting back on emissions in all senses as quickly as we can. And I mean, there's some evidence, for example, in Antarctica, that this region that I mentioned has in fact already crossed its tipping point. So there is a lot of uncertainty, and a lot of these processes we're still learning about them. But because of that, I think we really need to very rapidly get to the point where these targets are even more ambitious and cutting emissions quickly.
Rachel.
Yes, I just wanted to add to those wise words from Sebastian. So one of the things that climate change mitigation does is to reduce the rate of sea level rise. So we can't stop sea level rise because there's a commitment to sea level rise, but we can reduce its rate. And if you reduce the rate of sea level rise, the point is that it makes adaptation much easier in both human and natural systems. So, example, we're very worried about losing our coastal ecosystems to sea level rise, but they do actually accrete sediment naturally. And if we reduce the rate of sea level rise, then we can potentially maintain them because they'll be able to basically compensate for the sea level rise. But if the sea level rise is too fast, you get to a point where the rate of depletion exceeds the rate of accretion. So it's exactly as Sebastian was explaining about the loss of ice from the glacier. The loss of sediment exceeds the deposition rate, and then you lose your wetland. So decreasing the rate of sea level rise is really, really important. And obviously the same applies to human systems. The slower the sea level rise, it effectively means for human systems, you know, there'll be fewer and less severe storm surges to deal with. And that's much easier for the economy to deal with. And then there's more time to plan about, well, how do we actually deal with this? Well, actually, one of the best ways of protecting coastlines from storm surges is to protect natural ecosystems, to protect coral reefs. If you remove the other stresses on coral reefs, then they will persist for longer under climate change and also protect human systems and human coastlines from storm surges and sea level rise. So in fact, all of the actions you can do to mitigate and adapt to climate change, just as we're worried that all of these risks may interact, actually all of the things that humans, all the responses that we can do to help can themselves be made to interact synergistically if you plan them properly. You can also do it so that they actually act in conflict with each other. So it's really important to plan our adaptation and mitigation to get these win-win benefits from them both.
Well, thank you ever so much, Rachel. Right, we have another question, which is going to take us back to the AMOC. So I wonder whether this is perhaps in your field, Levke. It's the question is, how do we monitor or measure the AMOC on a yearly basis? What are the kinds of measurements and how accurate can we do this?
Yeah, that's actually a good question. It's kind of complicated given the size of the AMOC. I mean, as I showed you, it's basically spanning the whole length of the Atlantic. And in terms of the water masses that are transported, the AMOC is about the size that is 100 times as large as the Amazon River, which is the largest river on Earth. And it's kind of sluggish in the sense it's not like completely stable in one place. And also, if you look at different places in the Atlantic, it would not have necessarily the same strength everywhere. And what has been done as a really like international effort is that in 2004, there was like a whole array of measurement instruments installed in the Atlantic, basically covering the whole width, that is a few thousand kilometers of the Atlantic, measurement area after measurement area. And that was actually necessary to, at least for this latitude, give an accurate estimate of the strength. And because they're installed there, they actually give, I think, data every 12 hours. So that's pretty good and continuous data. And it is a really good estimate for the AMOC at that point. And we kind of believe that at least it does kind of co-vary with the AMOC strength at different places. But it is complicated. It's still one spotlight of the AMOC for this certain place. And of course, in terms of maybe early warning systems, in terms of changes of the AMOC, there's actually now a different area which was installed in the south of the North Atlantic, closer to the places where the steep water formation takes place, because this is of course crucial for the AMOC. But yeah, it's complicated, and also I do know that they sometimes struggle with funding, even though it's of course extremely important to keep this going, to keep measuring the AMOC, just in terms of knowing what's going on right now with the AMOC.
Great. Well, Levke, thank you ever so much indeed. And I think really that's probably all we have time for in terms of the questions. First of all, want to thank all of our amazing speakers today, so Sebastian, Levke, Niklas and Rachel. We're so grateful to you for contributing your insights derived from your research and your explorations on the scientific areas. We're really, really grateful, and it really has highlighted to me the incredible importance of us getting a grip on points. And Rachel, your opening remarks regarding, it's not necessarily about the worrying about the 4 degrees centigrade. It's actually our now increased understanding of just how terrible the risks are regarding tipping points, even within a smaller temperature rise. And therefore, we really do need to pay attention to these. So I would invite people, the audience, to the following session on cascading climate risks, which is, as I said, was germane to one of the questions posed. That session starts at 14:45 after our 15-minute break, and that will explore potential tipping points in societal reactions to climate impacts, cascades of interacting risks resulting in the financial crisis, conflict, political change, or a collapse in critical systems. And then I would also encourage people to just think about that question that was posed regarding, well, what might we actually do to sort of slow the systems down, and the research therefore that might be needed, well, the research is needed so that we at least know more about sort of options that we may or may not have to be able to do any of this in terms of looking at solar radiation management. And the Centre for Climate Repair, it's one of those thorny questions that actually we do want to grasp that nettle and do some thinking about. And we've got various events ourselves. The next one will be on the 19th of October. It'll be an online event, so do have a look at our website. If you just do a Google search on climate repair at Cambridge, that will help you. So again, I want to thank everybody, the audience as well, for your wonderful questions and for your participation in the session. And we look forward to seeing you at 14:45. Thanks ever so much indeed. Bye-bye.